Welcome, Hornets. In this video, we're going to be taking a look at the basic properties of limits that go just a little bit further than the last video. In these, we're going to be explaining why polynomials work the way they do. So we're going to start off with the first basic rule, and this basic rule is the idea of a scalar multiple. So we're saying that we have the limit as x approaches c of a basic function f, and we're going to call it L. We're then going to say that there's another limit also approaching c, and this is for the function g of x. We're going to call it k. Now, if I am looking at the limit as x approaches c for some constant b times our f of x, what we have to understand is that in this problem, this b value is called a scalar. Okay, so this is called the scalar property. And the whole idea is that we want to factor out and move this constant out so that we can work with our limit as x approaches c first. And when we're doing it, we end up doing it very quickly and pretty easily. So we have this situation, and we already know that according to our definition, this is the limit of c. And when evaluated, we have our scalar multiple of our limit. So once again, this is our first of our scalar, or our first of our properties. Now, if you look at this, let's just take an example. The limit as x approaches, let's go with 3 for 4x squared. Now in this problem, the 4 comes out. We then find the limit as x approaches 3 for x squared. This is our basic limit, and we know how to do basic limits. We've talked about it in the previous video, and we've also seen it in the video for this lesson here. Now, when we're doing this, all we have to do is plug in our 3. We get 9, and we have 4 times 9, and our limit is 36. Notice how it's a very basic process. We factor out the 4, we find our limit, and then we multiply. Scalar limit, or scalar multiple. Now, the second of our properties is that of a sum or difference. So the sum or difference property. Now, the sum or difference property simply says that if you've got more than one limit, let's say the limit as x approaches c for the function f of x plus or minus g of x, we are going to distribute our limit to both pieces. That means that I have the limit as x approaches c for f of x plus or minus the limit as x approaches c for g of x. And we already know what these are. We saw them from our basic information. Let's just remind ourselves over on the side. The limit as x approaches c for f of x, we said was L. And the limit as x approaches c for g of x, we said was k. And because of that, by direct substitution, I have L plus or minus k. Now, we do this quite often as well. If you think about it, when we're talking about a linear equation, let's take a look at one. The limit as x approaches 2 for the basic equation 3x plus 1. Now, we did these. We've seen them in our original review that we saw over the weekend. And now what we're dealing with is trying to work with multiple properties. Notice that there is a scalar and there is a sum. So we would first distribute our limit statement and look at it as 3x plus the limit as x approaches 2 for a 1. We know that the 3 has to come out in front, And we're looking at the limit as x approaches 2 for x, and then we are adding the limit as x approaches 2 for 1. Now, according to our rules, these are our basic rules, this just gets a 2. And according to our scalar rule, we multiply by that basic limit. This is also a basic limit, the limit of a constant. When we have the limit of a constant, at any value we approach, it is the constant. Notice it is the same thing as plugging in the 2 into the original equation, what we did when we were reviewing. When we did this, we end up getting a 7, and that 7 is my answer. The third of our rules is the product rule. The product rule is pretty much telling us that if I have 2, the limit as x approaches c for a product, f of x times g of x, please recognize this is not a composite. What we want to do is we want to distribute the limit. So we're looking at the limit as x approaches c for f of x, and we're multiplying it by the limit as x approaches c for g of x. And this gives us L times K by direct substitution. So let's just take a look at an example. Let's look at the limit as x approaches 1 for, let's say, a function called 3x. And we're going to multiply 3x by x squared. Now we know that this is going to be 3x cubed, right? And 3x cubed is a scalar of 3 times the x cubed. Well, the same thing should come out from this. When I take my limit as x approaches 1, I'm looking at the 3x. I'm then multiplying by the limit as x approaches 1 for x squared. Now, obviously, if you're approaching something else like 2 or 3, it's a little bit more obvious to see. You might want to try that on your own and just see what the results are for your own curiosity. I'm now going to take my scalar, which means that the 3 comes out. And then I multiply by the basic rule of x. This one is just our basic rule of our power of x, x squared. We know this is just 3 times 1, and we're multiplying by 1 squared. Our answer is simply 3. So notice I can simplify 3x times x squared and get 3x cubed and then evaluate it. Even if I were approaching 2, just look at it. 2 would give me 6, and this would give me 4, and I'd end up with 6 times 4 is 24. That's the same thing as 2 cubed, which is 8, times 3. So you got a lot of possibilities on what you're working with. Now, just because of our product, it happens that the quotient is also going to do the same thing. So if I have a quotient and I'm working with the limit as x approaches c for the function f of x over g of x, then I am really looking at the limit as x approaches c for f of x divided by the limit as x approaches c for g of x. Now, once again, we've seen an equivalent type of distribution of limits. Limit to every term, limit to the numerator and the denominator. And according to our rules, this turns out to be L divided by K. All right? So when we do these types of problems, I could simplify them just like I was doing in the previous problem with a product. Or I can do them separately and then combine them at the end. Now, these rules are going to be extremely important to us, especially when we're looking at trig functions. Think about tangent. Tangent is sine over cosine. We're going to need to do the limit of the sine and the limit of the cosine separately, and then put them together. Okay? This is going to be very important to us over and over again. Now, I'm not going to go ahead and do a different example of this rule. I'm going to leave that to you. The last rule that we have is the power rule or the exponent rule. Now, for our power rule, it says that if I have the limit as x approaches c for f of x, and I'm saying that this is to the nth power, that power can cause a problem. As a result, we take our limit as x approaches c for the inside piece, and then we apply the limit after. This would give us L to the nth. So we're going to now give you an opportunity to do a few of these problems. Be aware they are in your homework tonight, and then I will come back and we'll take a look at some more in our next video. This will be part 2, and in part 2 we're going to be looking at special limits. Thank you very much, Hornets, and be well.